Let x and y be non-empty subsets of the real numbers whose union is R and such that each element of x is less than each element of y. Prove that there exists an A in the real numbers such that x is one of the two sets. All x and r such that x is less than or equal to A, or all x and r such that x is strictly less than A. Okay, so we're going to split this up into three different parts here. We're going to split this proof up into three different parts. For the first part, we're going to prove that x intersect y is equal to the empty set. That is to say that the intersection of x and y is empty. That is to say that they are disjoint. And it might not seem like we need to prove this, but it'll become necessary for part 3 here. So, and for part 2, we're going to prove that x is bounded from above, thus implying by the least upper bound property that x has a least upper bound. And for part 3, we're going to prove that there exists what they asked us to prove, that there exists an A in the real numbers such that x is equal to x and r such that x is less than or equal to A, or x is equal to all x and r such that x is strictly less than A. Okay, so just to recap here, the least upper bound property of the real number states that if a non-empty set is bounded from above, then that implies that x has a least upper bound. So we know that x is non-empty because by hypothesis, x and y are non-empty. And we also know that by 2, once we prove 2, that x is bounded from above. Therefore, by the least upper bound property, x must have a least upper bound since it's bounded from above. Okay, but before we prove 2, let's prove 1 real quick here. So to prove 1, I'm going to switch colors just for variety here. So to prove 1, we want to show that x intersect y is equal to the empty set. So suppose, we're going to prove this by contradiction. So suppose x intersect y is not equal to the empty set. Well, if it's not equal to the empty set, that means the intersection is non-empty. So that means there must be an element in this intersection. So this implies that there must exist some u in x intersect y. And by the definition of said intersection, that implies that u is in x and u is in y. Well, if a u is in x and u is in y, then check this out. So we know that each element of x is less than each element of y. So u is in x. So that means since each element of x is strictly less than each element of y, this implies a strictly less than. That's important. They didn't say less than or equal to. They said less than. That implies that they mean less than, that implies that they mean strictly less than. So if u is in x, that implies that u is strictly less than y for each, this is the sign for each or for any, for each y and y. And u is an element of y. So this implies that u is strictly less than u. But this is impossible. U is equal to u. U can't possibly be strictly less than u. So this is a contradiction, implies a contradiction. Thus, if we were to suppose that the x and y are non-empty, the intersection of x and y are non-empty, is non-empty, then the intersection of x and y, then we arrive at a contradiction. Thus, so let me say that again. If we were to suppose that the intersection of x and y is non-empty, then we arrive at a contradiction. Therefore, it must be empty. The intersection of x and y must be empty. So we've proven 1. Let's just check that off here. We've proven 1. So let's prove 2. We want to prove that x is bounded from above. We want to prove, so x bounded from above. I'm going to switch colors again here for just more variety. So let's prove this. So let's take or first of all, let's talk about what it means for a set to be bounded from above. If we want to show that x is bounded from above, this implies that, well, I'm not going to say that this implies, but we want to find an r, r in the real numbers, so just any real number, such that x is less than or equal to r for all x in x. And this r, then this implies that r is an upper bound, which implies that upper bound of x, I should say, an upper bound of x, which implies that x is bounded from above. This is bounded from above. Okay, so let's find this r. So remember, way back at the top here, by the hypothesis of the problem, by the statement of the problem, each element of x is less than each element of y. So, if I have an element x, since each element of x is less than each element of y, we can say that if I have an element in x, then that means it must be less than each element of y. And I can also say that if I have an element in y, so given an element, we'll call it y prime in y, this implies that x, since each element of x is less than each element of y, that implies that x is strictly less than y prime for each x in x. And look at this. We've already done it. We've proven that x is bounded from above. That implies that y prime is an upper bound, upper bound of x. So, and the reason why we can say this is if we can find an element in the real numbers such that all x in the set that we care about, so all x and x are less than or equal to r. So we have, in our case, we have strictly less than, so that's fine. That still satisfies this property here. So we've proven too. We've proven that x is bounded from above, and therefore x has a least upper bound. So all that we have left is to prove 3. So let me clear the board to prove 3 here. So for 3, and I'm going to change colors again for variety here. Let's change it to green. So for 3, we're going to prove what they asked us to state. So I won't write it again, but prove that there exists an A and R such that x is one of the two sets. X is an R such that x is less than or equal to A, or x is an R such that x is strictly less than A. So we're primed to prove this by 1 and 2. We're primed to prove it. So I'm going to make a claim here. I claim that x is equal to x in R such that x is less than or equal to A, or x is equal to the set all x in R such that x is strictly less than A, where A is equal to the least upper bound of x. So if this claim were to be true, then that implies that there exists, since x has a least upper bound because it's bounded from above, then that implies, if this claim were to be true, then that implies there exists an A such that one of these two statements holds. Okay, so let's and I first, this claim didn't come out of nowhere. We can sort of see where this claim is coming from because we know that any element in x must be less than or equal to A if A is not in x, so where A is the least upper bound. So if I have a least upper bound, then least upper bound A, least upper bound of x is equal to A, then this implies that all x in x, for all x in x, x is strictly less than A if A is not in x, or x is less than or equal to A if A for all x in X, or X is less than or equal to A if A is in X. So this claim follows nicely from our knowledge of what it means for an element A to be a least upper bound of a set X. So that's where this kind of claim came from. It didn't come from out of nowhere. I didn't just pull it from thin air. So let's continue with this. So first I want to prove, before I prove this claim, I want to prove that for any element in R, for any R in the real numbers, R is in X or R is in Y, but not both, but not both, but not both. Okay, so we know that R is equal to the union of X union Y, because remember, that was what they stated. R, X and Y, whose union is R. So we know that R is in X or R is in Y. But what about this but not both bit? What is this not both business here? Well, we know that X by one, X intersect Y is equal to the empty set. Therefore, R is either in X or R is in Y. But by this statement here, but not both, but not both. Okay, so we've proven that. So that's under our belt. So we can use this later. So I'm gonna continue, and by using this, we can say the following. So the least upper bound of X. So let the least upper bound of X, let it equal B. We'll just call it B. Oh, I should say this in a different way. I should say let B equal the least upper bound of X. So that way I don't have to keep writing least upper bound of X. So let B equal to the least upper bound of X. Now, B is in R. That implies that B is in R, of course. So, since X is a subset of the real numbers, so B must be in the real numbers, since it's the least upper bound of X. So this implies by what we just proved up here, that B is either in X or B is in Y, but not both. So we split into two cases here. So for case one, B is in X. And for case 2, obviously B is in Y. Case 2, B is in Y. So for the case that B is in X, we want to prove, remember what we want to prove. We want to prove that this B, this least upper bound, is such that X is equal to all X in R, such that X is less than or equal to B. I use B here. We could have used A. It doesn't matter because this is just arbitrarily named. It's just a naming thing. But so B is in X. So we want to prove that X. So let me write this here. We want to prove that X is equal to the following set, all X in R, such that X is less than or equal to B. And the reason I chose that to show, in this case, the reason I chose to show that X is equal to all X in R such that X is less than or equal to B is because I know that I'm kind of hinting at the fact, or I know that later on I'm going to use the fact that since B is an X, that means that, and since B is the least upper bound of X, then that means that all X in X is less than or equal to B. But we'll see where that comes into play later. So to prove this, remember to show a set equality here, we have to show that X is a subset of this guy, X in R, such that X is less than or equal to B. And we have to show that all X in R such that X is less than or equal to B is a subset of X. So let's prove this first, that X is a subset of this guy. So let x be an x. Let x be an x. If we can show that this x and x is also in here, then we've shown that any x in here, must also be in here. Okay, so let's do that. So let x be an x. That implies that x, well, we know that x is an r, because x is an x. And since x is an x is in big X is strictly less than or equal to b, since b is the least upper bound of x. Since b is the least upper bound of x. So that's nice. But look at this. X is an element of R, and x is strictly less than or equal to b. So therefore, x satisfies the property of being in this set. X satisfies all the conditions of being in this set right here. So therefore, x is in the set of all x and R such that x is less than or equal to b. So therefore, that was fine. We proved that case. We proved that x is a subset of this set right here, because any arbitrary x in here must also be in here, as we've just proven. So let's prove the other way, where we need to prove that this set, all x and R such that x is less than or equal to b, is a subset of x. Well, to prove this, so we're going to take any element in this left-hand side set. I'm just going to say left-hand side set. That implies that x, take any element x, and that implies that x is less than or equal to, let me mark off some more room here. That implies that x is less than or equal to b. And now we're going to suppose, so remember, x can either be in y or x can be in x, because we proved that up here. We proved that upstairs. Any element in the real numbers must either be in x or in y. So suppose x was in y. Well, since each element in x must be strictly less than each element in y, then, and since b, our least upper bound, by our first case here, b is in x, this implies that b is strictly less than x. But I just said that x is less than or equal to b. So this is a contradiction. It must be that x is in x. So we've proved that they're subsets of each other, so therefore we've proven that they're equal to each other. So, for case 2, we want to prove that x is, well, first of all, for case 2, we have that the least upper bound, b, is in y. The least upper bound b is in y. So we prove that x, in this case, x is equal to the set x and R such that x is strictly less than b. So now, let's prove this. So first we're going to prove that x is a subset of all x and R such that x is strictly less than b. So to do this, let x be an x. This implies that x must be strictly less than b, since b is the least upper bound, or actually since b is the least upper bound and b is not in x, but really we can also say this fact because because b is in y, and each element of x must be strictly less than each element of y. So since b is in y, we didn't even need this part. Since b is in y, we know that x must be strictly less than b. So we're done. We've proven that any x that we can choose in here must also be in here. Oh, by the way, so since x must be strictly less than b and x is an element of R, x is in R, and that implies it satisfies the property of being in this set right here. So therefore it is in that set, and therefore any arbitrary x in X must also be in this set right here. So now, let's go on to prove that X contains, X is, X contains the set X and R such that X is strictly less than B. So, take an X in our right-hand side set here, X and R, such that X is strictly less than B. And suppose we're going to do the same thing we did last time, and suppose X is in Y. Suppose X is in Y. Well, we know that X is strictly less than B. We know that. And if we were to suppose that X is in Y, this implies that every element of X, so every element of X, so I'm going to say every what letter haven't I used? V in X is, or has the following property. By hypothesis. Remember, way up here. Each element of X is less than each element of Y. For every V in X, V is strictly less than X. Since I'm supposing that X is in Y. So since each element of X is less than each element of Y, and since X is in Y, that means that each V in X, every element of X, is less than X. But this implies that X is an upper bound. But look at this. But X is strictly less than B. Therefore, X is an upper bound that's strictly less than our least upper bound. That's strictly less than, X is an upper bound, that's strictly less than our least upper bound. Since B, remember, B is our least upper bound of X. Thus, this is a contradiction. Therefore, X is in X. And we've done it. We've proven that there exists an element, namely the least upper bound of X, such that X is equal to one of the following two sets.